Hello and welcome to this video lecture. So in this lecture, we will be discussing higher order ordinary differential equations. So as I had indicated before, this will be a relatively short discussion, as we'll find out if we can deal with a particular form of differential equation, specifically a form that we've been working with now for quite some time, which is an LTI ODE. So if we have an LTI ODE, we can readily expand or extend what we have already learned to these higher order ordinary differential equations, as you'll see here shortly. And we will quickly see that this discussion is a relatively short one. So even though we're talking about something that appears to be considerably more complex than what we've discussed so far with first order and second order differential equations, it turns out that we have already laid a very good foundation for talking about these higher order ODEs, specifically LTI ODEs. And I'll get that in your notes in a moment. So let's go ahead and introduce the discussion. So clearly, based so far, or let's say it this way, based on our understanding that we have developed so far, of first and second order ODEs, clearly we're now going to extend what we've been discussing to higher order ODEs. Here I'll just say it as now, we can now investigate. Higher order ordinary differential equations. And so let's go ahead and just define it. I know I've said it and it's implied in that statement, but let's state it explicitly. So this, of course, is where we're dealing with differential equations with derivatives higher than second order. So, as I've said, when we're looking at these, or this particular class of differential equations, it turns out that my M got a little messy there. If you'll give me 1 second to clean that up. So it turns out then that the methods that we've discussed before again for, of course, our lower order, messed that one up too. Sorry about that. Okay, back in business. Lower order equations, of course, generally apply equally well to these higher order systems. And here I'm specifically referring to the idea of the characteristic equation that was associated with an assumed solution, as well as this idea of linear differential operators. So both of those we've already developed. Now let's, of course, capture, though, that we developed them for. Non-homogeneous differential equations as well as the homogeneous case and the use of initial conditions to excite the system. So we can use these methods for our homogeneous case as well as the non-homogeneous case. One of the nice things, though, that for the non-homogeneous case is that if we elect to go with the characteristic equation method, I'll just note that you can use the method of undetermined coefficients for this particular case as well. Because remember that when we use the method of undetermined coefficients, the assumed form of the particular solution was independent of the form, or let's say it this way, the exact form of the differential equation, just as long as it was LTI. So as we can see, we can again use the method of, or let's say it this way, the characteristic equation approach or the linear differential operator approach, and the various tools that we developed for both of those methods apply equally well. Now, we can use the method of undetermined coefficients to find the particular solution, and for the homogeneous case, we can use the roots of the linear differential operator or the characteristic equation if you prefer. since the two are the same. And that can be used. To determine clearly the basis functions for clearly the homogeneous solution. Again, assuming linear time invariant, i.e. LTI, equations. And then, as always, of course, so we can use the linear differential operator to come up with the various basis functions, and then the most general form of the solution for the homogeneous case. So we'll say in its most general form. Is a linear combination let me get my B in there. Is a linear combination, of course, of those basis functions. And so we can see that the approaches that we used before, and even though I tied generally the method of undetermined coefficients to the approach associated with the characteristic equation, clearly we don't necessarily need to work exclusively or use the method of undetermined coefficients exclusively for that particular approach. For the characteristic equation approach, we can use the method of undetermined coefficients to find the particular solution at any point when we want to. So with, again, the exception of some of those times where we have issues with the one of the basis functions from the homogeneous solution stepping on the assumed solution for the method of undetermined coefficients. That's where we can, of course, run into a little bit of trouble, as we saw. So we can go ahead and use those approaches, the characteristic equation approach, the linear differential operator approach. But now we can go ahead and, which we developed for second order specifically, but we could see it could be used for first order equations as well. We can extend that to higher order differential equations. So since it is possible to have now n roots rather than just one root or two roots, depending on if it's a first order LTI ODE or second order. Now we can have n roots. So expressing this, assuming a linear differential operator, we have d plus r1 times d plus r2, all the way on out to d plus rn, all of that times x is equal to 0. Now, here, as you can see, I'm only showing for convenience first order roots. Just to make writing it down a little bit easier. Clearly, we can have second order roots as well, but what's a second order root? A second order root is simply a way to write roots so that we're dealing with just real numbers. Because a second order root can be expressed as two first order roots, where those first order roots are just complex conjugates of each other. They are complex, the roots are complex. If we wanted to allow for, of course, complex numbers here rather than just these real numbers. But to make things a little bit easier, just to keep things, keep the notation a little bit simpler, I'll just go ahead and assume that we're dealing with first order roots. And so that's it. You go ahead, you find the linear differential operator, you factor that linear differential operator, you get the roots, and then we start working with the solutions that we know are associated with those particular roots, and that's it. Now we're just going to have more roots rather than one root or two roots, or a single second order root if it was a second order ODE that has potentially complex or purely imaginary roots. So with that, clearly we can see that each root now captures its own, here I'll say a, basis function. So then if we look at d plus rm, if we just choose one of those roots, whichever one it is, and we multiply by x to get 0 because we're dealing with a homogeneous LTI ODE. So this is a homogeneous solution, of course, since d n minus 1 plus c1 d n minus 2. Now notice that I've taken out one of the quote unquote d's here because I factored it out as we have done before, plus, and then just go doot, 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 all the way on down to cn minus 1. And then all of that will just be multiplying our d plus rm acting on x, which of course since we know this is true, this will be equal to 0, and I'll just slide this over just a little bit. And this whole thing is equal to 0, satisfying the homogeneous ODE. Homogeneous form of the ODE might be a better way to say it. So here I'm just showing everything that's left over, the remainder, if you like, when I have factored this out. Or what remains might be a better way to say it, when I have factored this out. Okay, so this is, of course, from the other n-1 roots. Oh, let's get my r in there first. Okay, back in business. Roots, but of course here I'm just representing them as they would be multiplied out, or as they are multiplied out. Since in this particular case, I am assuming I don't know what they are. At this particular point, I just know D plus RM. Okay. And so then I can state, okay, since so this whole thing is equal to 0, and then just kind of continuing on with that statement, that's true regardless of course, as we have seen, of what D n-1 plus all the way on out to C n-1. Regardless of what that is, since, of course, we already know that D plus RM operating on X will give us a 0. So everything else here is operating on a 0, and we're just going to get another 0 since operating. On 0, clearly from D plus RM times X equals 0, clearly yields 0. And so then we can find the basis function associated with D plus RM, and then we can go ahead and go back to the original linear differential operator and then factor out another root and repeat that process again and then again and again until we have gone through all of those roots. So I'll sum that up as saying, clearly, all we're doing is now just repeating this process. That's the only complexity associated with these higher order LTI ODEs. We just have to find more roots. That's it. So we repeat it for all roots to find all the basis functions. And then, of course, we can, as we have in the past, form that linear combination of those homogeneous basis functions, and then combine that with a particular solution, and we are set to go. So let's go ahead and capture the fact that when we're dealing with LTI systems, and I've already gotten into this a little bit or discussed this a little bit in this lecture, it turns out that the roots, of course, as we already know, will only come in two forms. No matter how high the order of the LTI ODE is, we only get two forms of roots, and we can even argue that really there's only one form of root. But let's go ahead and just work with this idea that we have first order roots, which of course is the one we just saw. Here again, I'll capture it as D plus Rm. And then we'll also say that there are second order roots, though we can recognize that we only have, if we choose to, we can only have, or we only really need first order roots provided that we allow those roots to be complex. That's it. But there are some advantages that we will see later on, allowing for these things called second order roots that are just the result of multiplying two conjugates together. So the form of a second order root is d squared plus amd plus bm for our second order root. And so you can see why we can now talk about higher order systems, because we had to first figure out what was going on with first order systems and then second order systems, because we can now see, so we had to complete those discussions because we can now see that these higher order systems can be broken down into nothing but these first order roots and second order roots that we can see were originally associated with first order systems and second order systems. And that's it. So once we got those discussed and got those developed, these higher order systems, again, LTI ODEs though, these higher order systems just come right on along with the development that we have already worked through. So let's go ahead though and capture that the overall linear operator, as you can guess from our discussion of the roots that are developed from that operator, so that that linear differential operator, of course, can be constructed from those very same roots, since the roots came from that linear operator. So if we have our linear operator, dn d to the n plus c1 dn minus 1 plus all the way on out to plus cn minus 1, we can see that this is just going to be equal to then dr1 times d plus r2 all the way on out to d plus rn. And then, of course, as I have stated verbally, but I don't think we've gotten it in your notes, then, of course, the basis functions can then be found directly from these roots. Whether we go through solving the homogeneous differential equation associated with each of the roots individually to figure out the solution, or whether we just recognize that we've done that enough times, and I think we've already done that enough times, that we can then just map the constants associated with that particular root to the specific constants associated with the basis function, the form, let's say it that way, the form of the basis function associated with that root. And at this stage of the game, you're probably getting good enough at this that you'll probably take the latter approach, where you see a first order root, you're already starting to recognize that's just an exponential response. So, and then of course, if we have a second order root, or, well, let's just say it this way, either a second order root explicitly written out in the form that I have above, or whether we write that second order root as a product of two first order complex conjugates, doesn't really matter. Okay, so with that, let's go ahead and work an example so that we can see how this is done. So let's say find the system response as we usually do. And here we are now given, now of course this is, I'm going to try to keep things relatively manageable here, because higher order ODEs can start to get a little busy. So we'll have, so I'll just go to a third order. So we'll have d cubed x dt cubed plus 3 d squared x dt squared plus 4 dx dt plus 12 is equal to 0. Now for this particular problem, I'm going to run with the characteristic equation approach. Again, the characteristic equation that is associated with an assumed form of the solution. And so clearly our characteristic equation in this particular case is just going to be, so we have our third order derivative multiplied by 1, of course, and so we'll get an s cubed. Then we have 3 times the second order derivative, so it's going to give us a 3s squared, 4 times a first order derivative, 4s, plus, of course, we have, oh, I almost forgot my x. My apologies. Because with that 12 there, that is not a homogeneous differential equation. Let's go ahead and get rid of this and pop in my x. There we go. And then plus 12, and then that whole thing is equal to 0. Now we can take some time to figure this out, but I think we'll see, or you can see pretty quickly, that the roots are s plus 3 and s squared plus 4. All that being equal to 0. So we now know that we get an exponential component to the response as a result of having that first order root. And so we can have a C1 e to the negative 3t. And then for this second order root, and in this case, we don't have a middle term. And so that means that there is no, and you can see it from here as well, right? We're going to get s squared is equal to -4. There's no real component associated with that. Those are purely imaginary roots, which means that we have no exponential component or exponential influence associated with that particular response. So then the basis functions for that particular second order root is C2 times cosine. And of course, remember, we have to take the square root of this particular value when we have just purely imaginary roots. We take the square root of that value, which gives us 2, and that appears in the argument for the cosine function, 2t, plus C3 times sine 2t. And of course, oh, what am I saying? Too much homogeneous on the brain. My apologies. That's not equal to 0, it's equal to x. There we go. Because that is our most general form of the solution for this higher order LTI ODE. A linear combination of all the basis functions. And so we can see that we just take what we've been doing all along, figuring out what the roots are associated with the characteristic equation, and then forming basis functions from those roots. We've just been limited to first order and second order systems, and now we just do exactly the same thing with higher order systems. You just find the roots, you figure out what the basis functions are from those roots, and then you just go ahead and you form your linear combination of those basis functions. Now, just to show you that this actually works out, let's go ahead and do our double check. So if you are comfortable with what we have been discussing before, and hopefully you've seen it enough times now that you are, this really shouldn't be a problem for you at all. So, okay, let's go ahead and take a look at x dot. We get a -3 c1 e to the -3t. And then for cosine, we're going to get a negative sign here. So we get a -2 c2 times sine 2t. And then sine will go to a positive cosine plus 2 C3 times cosine 2t. Now, unfortunately, we have to keep taking derivatives, right? That's the nature of these higher order systems, so I'll apologize in advance for that. It does get a little tedious taking derivative after derivative after derivative, but it really isn't that hard, just kind of boring. So my apologies for boringness. So you'll see very quickly that we get a 9 C1 e to the -3t, then we get a plus, actually no, in this case, we still stay with -4. Because that sign just goes to, so -4 C2, and that sign just goes to a cosine 2t. Now this one goes negative, and we get a -4 C3 sine 2t. And then last but not least, we have our third derivative of x. And so we get a -27 c1 e to the -3t. That cosine again goes negative, so, or gives us a negative sign. So now we get a plus 8 c2 times sine 2t. And then our sine just goes to cosine, so we get a -8 c3 cosine 2t. Okay, and now we get to plug that into our original differential equation up here. So I'm not going to show plugging in the derivatives directly. I'm just going to go ahead and multiply everything on out by the associated coefficients for the second order and first order, and the function itself. I'm just going to multiply those coefficients on out if everybody's okay with that. So we get negative 27 C1 e to the negative 3t plus 8 times C2 sine. So this, of course, is our third order derivative, 8 C3 cosine 2t. Okay, so we got our third order derivative in there. Now let's go ahead and multiply everything through by this 3. And so then for our second order derivative, and so then what do we get? We get plus. Actually, let me move that over if you don't mind. I think it will make it a little bit easier rather than indenting it because we're just going to be lining all these up anyway. So plus. So again, I'm now multiplying our second order derivative by 3. So we get a positive 27 C1 e to the negative 3t minus a 12 times C2 cosine 2t, and then another minus 12 C3 times sine 2t. And then we have our first order derivative multiplied by 4. So then we get a negative 12 C1 e to the negative 3t minus 24 times C2 times sine 2t. My mistake. So that's 4 times. Should have been an 8. My apologies. I already had 12 on my brain. Or in my brain might be a better way to say it. There we go. Okay, so going back, this one is multiplied by 4, so that's going to give me an 8. There we go, looks better. Plus then another 8 times C3 cosine 2t. And then last but not least, we have 12 times x. So remember, this is x up here. And so then we get a plus 12 times C1 e to the negative 3t plus 12 times C2 cosine 2t plus 12 times C3 sine 2t. And now we get to do every mechanical engineer's most favoritist thing, which is, of course, canceling. So clearly this cancels with this, which is why I wrote it in this particular form. Clearly this cancels with this. Now here in the, with the sines and cosines, we have to do a little bit of, hopping over terms. So clearly this cancels with this, and this cancels with this. And we can see the same pattern developing in this third kind of column, if you want to call it that. And then this cancels with this, and sure enough, we get 0. We get 0 from a third order LTI ODE. And you can see how simple it was to form the general solution, the homogeneous, let's say it that way, the general homogeneous solution for that particular differential equation. You can see that all we have to do is follow the same processes that we developed before, figuring out the roots associated with either the characteristic equation or the linear differential operator. And here I'll use air quotes for roots because, of course, the linear differential operator itself doesn't really have roots. You just go ahead and find those roots, and based on those roots, you go ahead and develop your basis functions. And then from those basis functions, you just go ahead and form your general solution by forming a linear combination of those basis functions, just like we've done time and again for first order and second order LTI ODEs. So hopefully you can see this wonderful extension and how powerful it is. Because initially you might have thought, well, this is pretty limiting. All we're able to talk about are first order and second order. How about fifth order or seventh order or whatever? And now hopefully you can see, again, provided that they are LTI ODEs, it doesn't really matter. We can go ahead and just, as long as you're willing to find roots, we can just go ahead and find the roots of that particular expression, and then we can then find, let's say it that way first, the individual basis functions, and then we can form the linear combination of those basis functions. Oh, and then of course, that's assuming the homogeneous solution. And of course, we can go back to our old methods. As long as they work reasonably well, we can go back to our old method of undetermined coefficients for finding the particular solution. So hopefully you can see that these higher order LTI ODEs really aren't a problem. You already know how to do them. There's nothing to worry about, even though on the surface they might have appeared considerably more complicated, considerably more complex. It turns out they really aren't. So with that, I will go ahead and call this video lecture a wrap.